Okay, so you're on a video call, right? And you drive through a tunnel, but your connection doesn't drop. Ever wonder how that's possible? Well, today we're going to talk about the unsung hero of 5G that makes it all work. Just look at this number for a second, plus or minus 1.5 microseconds. I mean, that is a sliver of time so small you can't even really wrap your head around it. But here's the crazy part. If you get this tiny number wrong, our entire 5G world comes to a screeching halt. So, how can something that small be the make or break difference between a perfect, seamless connection and, well, total network failure? That's the big question we're diving into today. And believe me, the answer is pretty surprising. Okay, so here's the deal. To stop all the different 5G signals from basically crashing into each other, every single base station has to be perfectly in sync. I mean, they're all dancing to the exact same beat, and they have to stay within that tiny 1.5 microsecond window. This whole thing is called phase and time synchronization, and for 5G to work at all, it's absolutely critical. So here's the catch. Where does our entire 5G network get this perfect rhythm? From GPS signals, beamed down from space. But, and this is a big but, those signals are shockingly fragile. You've got things like solar flares, just bad weather, or even intentional jamming, any of which can cut that lifeline in an instant. So you gotta ask, what happens when that GPS signal just vanishes? Does the whole network just collapse? Well, no. And this is where our hero, a system called Holdover, steps in. You can think of it as the network's own personal insurance policy.
So what is holdover? Put simply, it's the system's ability to keep ticking along, maintaining accurate time all on its own, using its local clock after that external GPS signal is gone. It's kind of like a pilot who loses all contact with the ground and has to fly purely on instruments. The plane keeps flying straight because it has its own internal system to rely on.
All right, let's break down exactly how this works. First, you're in what's called locked mode. Everything's great. The system's internal clock is perfectly synced up with that GPS beat. But then, bam, the signal is lost. Now, the system is totally on its own. And from that very second, its internal clock starts to wander, or what we call drift, away from the correct time. So, the ability to survive this drift, it really all comes down to one thing: the quality of that internal clock. The technical term for it is an oscillator. And choosing the right one, well, it's like choosing your champion to go into battle against this relentless creep of time error. And this table here lays out the options perfectly. You know, for something like a small cell that just needs to survive a couple of hours, a standard OCXO, that's an oven-controlled crystal oscillator, is totally fine. But for a big outdoor macro cell tower that needs to hold on for, say, 8 to 12 hours, you've got to step up to a double OCXO, which is just a much more stable version. And for the really, really mission-critical stuff, that's when you bring in the undisputed champion, the CSAC, or chip-scale atomic clock. It's literally like having a tiny, perfect atomic clock on a single chip. So yeah, it really just boils down to a simple trade-off. Are you looking for a cost-effective solution that can handle a short-term outage, or do you need that top-tier, mission-critical performance that can keep things running for days on end? It's simple. The better the clock, the longer your network stays alive. So what exactly are these little clocks fighting against? Well, there are two main enemies. The first is what we call quick drift, and that's caused by temperature changes. I mean, even a tiny, tiny shift in temperature can start to throw the clock off. The second enemy is long drift, which is basically just aging. Over time, the physical quartz crystal inside the clock, it actually degrades, causing it to slowly but surely lose time. And just to give you an idea of the scale we're talking about here, check this out. These clocks are measured in something called parts per billion, or ppb. Now, a drift of just 1 ppb means the clock is losing 1 nanosecond of time every single second. It's an unbelievably small error, but man, does it add up fast. Okay, so this has all been kind of technical, right? But how does this microscopic battle against time actually affect us in our daily lives? Well, the consequences are massive, and they touch pretty much every major industry you can think of. Let's start with the most obvious one, our phones. Without good holdover, the second that GPS signal disappeared, you'd get instantly dropped calls and failed data connections. It is literally what keeps your call connected when you drive through that tunnel. Now, think about our power grids. They're full of these special sensors called PMUs that have to be perfectly synchronized to keep the grid stable. If they lose their time source and drift apart, the whole system can become unstable, and that can lead to a cascading failure. Holdover is the fail-safe that prevents that. It literally helps keep the lights on. Okay, what about the world of high-frequency financial trading? Every single transaction has to be time-stamped with insane microsecond precision. And this isn't just for fun, it's actually required by law to prevent market manipulation. So if the master clock goes down, holdover is what ensures that trading can continue legally and fairly. It prevents millions, sometimes even billions, in losses. Then there's military and defense. For them, operating in an environment where the enemy is actively jamming GPS signals, that's not a what-if scenario. It's a reality. So holdover becomes absolutely mission critical. It allows communications, radios, and radar systems to keep working even when they're completely cut off from the outside world. And finally, let's look at the smart factories of Industry 4.0. You've got all these synchronized robots and machines working together, and they all rely on a perfect network clock to coordinate their movements. If that clock fails, holdover is the failsafe. It's what prevents dangerous collisions between robots and avoids super costly shutdowns on the assembly line. All right, so let's bring this all back home. Why does this tiny, almost obsessive-compulsive little timekeeper inside our machines matter so much? Honestly, this chart pretty much says it all. The level of precision you need for just a 4-hour holdover in a 5G network, it's 100 times more strict than what we needed for older telecom standards. The demands of our modern connected world have just pushed timing technology to a completely new level. And when it fails, the consequences are very, very real. Just think about navigation for a second. If a system that's lost its GPS signal has a time error of just 1 single microsecond, its calculated position could be off by 300 meters. We're talking about the length of 3 football fields. That's the difference 1 microsecond makes. When you really think about it, our entire hyper-connected world, from our phone calls to the stock market, all the way to national security, it's all balanced on the microscopic ticking of these tiny unsung heroes, silently, constantly fighting that battle against drift and decay. And that leaves us with one final big question. We're demanding more and more from our networks every single day, right? More speed, more data, more instant connections. But what happens when the physical limits of these tiny clocks are finally reached? What happens when our demand for perfect instantaneous time finally outpaces what our technology can actually deliver? That's a question we're all going to have to figure out, and probably sooner than we think.